Hello everybody, today we'll be doing search a 2D matrix. Write an efficient algorithm that searches for a value target in an m times n integer matrix. This matrix has the following properties. Integers in each row are sorted from left to right. The first integer of each row is greater than the last integer of the previous row. So the first integer of each row is greater than the last integer of the previous row. So this item will be greater than this item. So basically what's going on here with this matrix is that everything is in order, like this. Now, what we can do immediately, what we do know, is that if we just search everything by row, right? If we do a binary search at each particular row, we will be able to determine whether the item is in the row or not. We can also check the smallest item and the biggest item to determine if it is within range. So I think that's the best idea. So we'll just have to do a binary search that is vertical and then do a binary search that is horizontal to get our answer. So let's take a look at this example here. In this example, we were not able to find the value 13 because 13 does not exist. And in this one, we found 3, which returns true. So that's how it works. So those are two cases. Let's think about some edge cases here. Well, in this case, when we're working through LeetCode problems, we don't have much say over what sort of algorithm that we're trying to solve exactly and what are the parameters that we can set out for ourselves, unlike an interview question. So basically what we need to do here is look at the constraints that are given to us. And the constraints are m equals the matrix of length, n equals the matrix of each particular row length, and each particular matrix is going to be at least one item. So the smallest thing that we can possibly do is this. One item of one row and one column. That is the smallest item that we can possibly get. So the target is 0. And that will return true. Okay, the last point is minute because we don't really care about what the items are like inside the matrix. Okay, so how are we going to do this? Is that we're gonna, like I said, use the binary search. So what type of time complexity were we looking at when we're thinking about binary search? Well, it's going to be log of n plus log of m. That's binary search time. And that's what we're gonna do. So that's the time space complexity. Time complexity and the space complexity actually is O of 1. Because we're not storing anything. We're just taking a look. We're viewing. So we just need to use some variables to hold some pointers about the left and right, top and bottom. The easiest way to do this right now is, of course, m plus m. That is the easiest way, is just to search through the entirety of this particular item. So yeah. Why is it m plus m? It's because suppose you have like row of size 2 lengths, and m would then be 2, right? And you would have to search these items anyways, like left and right. So that would be O of m plus O log n. So many ways to do this. And so let's keep going. Let's play. So that is the match. Is going to be binary search. And the plan is to first start at the middle row eliminate half the possibilities using binary search. So if we use a binary search and we search this middle row between 10 and 20, right? That means that if our target is within that or outside of that target, whether it's greater or lesser, we can eliminate half the items. So all the items above this line, let's say it's a bigger item, we will not look at that anymore. So because we're not looking at that anymore, we have basically cut the number of items that we need to look at in half, which is a log. We basically log an M operation here. 2. Once we find the row, we use binary search on that particular row. 3, if we find it, we return true, else false. So how does binary search work? Well, we have a left and right pointer, and we make sure that we either will move the pointer up and down or left and right to eliminate items, but as long as the left and right pointer does not cross. Left and right pointer is left pointer is less than right pointer, and of course the up pointer, the top pointer, is less than the bottom pointer. Yeah. So anyways, continue, else stop. Okay, I think that's all. I think we should start implementing now, as we need to continue this video and finish it off, right? So here's our understanding and implementation. Okay, let's just, take a look at what we can do and see what happens. So let's define a binary search here. And let's take, well, it's not, I don't know if it's important to define the binary search. Let's just do a top bottom equals the top of this. Well, let's see. The matrix is going to be like this. So essentially, visualization is very important. Okay, so the top item, the top, I think, row is going to be at 0. The bottom row is going to be the matrix, the length of the matrix minus 1. Okay, so we found that. Great. Yeah, so we don't have to deal with the left and right yet. We'll deal with that later, but just in case that we forget. So left starts at 0, and right does length of matrix at 0 minus 1. As you can see, 0, 1, 2, 3, that's our right pointer, and that's our left pointer. Right here and here, it's the same for the whole matrix. And our top matrix is here, our bottom is here. Okay, this is a very good visualization for our program. Let's keep shifting our items down so we have room. All right, next step. Once we have this, we want to start at the middle row and eliminate. Okay, so while top is less than bottom, the midpoint is equal to the top, because we only have 100 rows and our target is very small. We can just do, well, not because the target is very small, because the range is very small. We can do a top plus bottom divided by 2 to get our average. That's our midpoint. So with the midpoint, we can find out if mid of the middle value of the first item is greater than our target, and the mid of our last item is less than our target. When we know that, that means we have found our midpoint. So we do a break here. We're good. Else if, let's say it's less than our mid at 0 target. Let's say it's less than target. That means it's also less than our last item here. So we want to bring our bottom pointer up to nearer to the top so we can eliminate the remaining items down here. So bottom is going to be equal to mid minus 1. Else, that means we just have to move the top down between mid plus 1. And so on and so forth until we break out of this loop. Okay. Now, to eliminate the answer, to immediately know if top is greater than bottom, that means we did not find the item. We did not find it. In between any row. Okay, well, we're going to return false immediately. Right. So let's check that. So we were looking at 13. So this should return false immediately. And let's return true if we found it. This should not return true. Oh. Also, this should return true because it's within bounds. Let's try 62. 62 is out of bounds, or less than 1. Less than 1 is also out of bounds. Those two items should be out of bounds. Oh, what happened here? We made a error. That's good. Let's keep testing. Okay, not an iterable subscript. Ah, I see. That's a problem, because what we've done is actually not what we need to do. We needed to do the matrix at the mid. So my bad, a little bit my bad there, and yeah, it's like that. I think this should be fine. Oh, no, the output is true. That means we made a mistake somewhere. That means this actually needs to be more specific than I thought, which is properly the case. So this is -1 is greater than the target. So this last item is greater than the target, let's say 7, then we move the top down. So sorry, give me a moment. Let me think. So matrix midpoint 0 is less than the target. We're looking for like 60, right? So we move the top down, right? Okay, I'm a little confused here. So let's say this is greater. This item is greater than our target. What happens then? Let's say our target's 23. Our target is 23, and our midpoint is here. Our target is less than 23. That means we should move the item the top down. If we're looking at a 3, and if this is greater than a 3, which it is, then we should move the bottom up. Okay? So if this is 23, then if this is 23, and we have 20, and our target is greater than this, then we should move our top down. Okay, that should do it. Let's run it. It's still returning true. I'm not sure why. Let's print out our top and bottom. Okay, this is a debugging phase. I'm gonna pause the video and I'll do some debugging here and see what's going on. Okay, I think we found the error here. It's the less than or equal to sign, because if they are of the same item, the top and bottom is the same, then there will be no movement. And that's why the top and bottom was equal. So we set the equal sign here just so that it does not, so that the top can move past the bottom. And I think in some cases, I mean, in most cases, we do want the top to be less than or equal to the bottom, because, I mean, top and bottom could be the same, and that would give us that particular midpoint that we didn't see earlier. Okay, with that, return false, and I'm expecting -1 to return false as well, because it's out of bounds. Okay, now anything inbound, let's say 15, even though it's 26, anything inbound should return true. Uh-oh, we have a problem. I think we have an infinite loop here. So because this is an else if, let's just set this as else, and let's go from there. "26 is supposed to be inbound, and we have an issue because it's not inbound. We did not break properly. So let's look into that bug. Okay, great, we found the bug. So the bug was here. We just swapped the signs here. The problem was that this item, if this item is less than the target and this item is bigger than the target, that means it's in between. So the problem was that I think we should reframe this, and let's say the target's in between and the target is less than the top, and that way less than or equal to, actually. That's what we actually want. and that way we don't skip over things like a 10. Like, I mean, without the equal to, I think we would skip over things like 10. Let's run it again, and we are good to go. We are seeing what we want to see. We are getting what we want to get. This is perfect. I think we have enough testing to be done with this portion, and we're going to move on to the next portion where we have to find it in the row. So while left is less than or equal to right, we're going to get the mid, which is equal to left plus right divided by 2. If matrix at this, so row is equal to mid. Let's save that. And at this particular row, let's check the mid. If it's less than the target, if let's say 16 is less than the target, then the target must be greater. So we need to do a left equals mid plus 1. Else, if the matrix row at mid is greater than the target. So this item, let's say our target was 11 and we found 16. So 16 is greater than our target. That means we need to bring the right in, mid minus 1. Else, basically, if matrix at row and mid is equal to the target, that means we have found it. Return the target, return true. Otherwise, the left has crossed the right and we have to return false. Let's run this code. It should return true. And we are good. And let's find something like a 14, a 15, something like that. It should return false. Perfect. Now let's run some example cases. Great, that we got all the results that we wanted. Let's submit and see what happens, because I don't know exactly what happened, but it looks like we might have a good answer here. We might. There might be other bugs that we don't know about. Let's check it out. Oh, we got it. No, that's great. So we have solved the problem. With this print statement, it slows down our algorithm a little bit. Let's submit again to speed it up. Great, we have a very fast solution. So with that, we can do our times and space evaluation, which is time again is O of log of M, because we did a binary search on the bottom, on the top to bottom. Then we did a log of N, because we did a binary search on the row. Also, for space, as you can see, we only use the top, bottom, left, and right pointers, and a row pointer. That means it's an O of 1 space. So with that, we have completed the problem called search matrix. I hope you enjoyed the video and implore you to try this problem yourself. I like the problem a lot myself, and it was pretty fun. So I hope you check out this problem and that you enjoyed the video. If you like the video, please like and subscribe. And if you want more, check the link in the description below. If you have any questions, please comment. I'll see you next time.